In this video, we're going to look at the product property of logarithms and where it comes from. So the product property of logarithms is given by log base b of m times n being your product, is equal to log base b of m plus log base b of n. And we'll see that there's a relationship between the product property of logarithms and the product property of exponents. First, what I want to do is look at this power table of 2 up top. And so if we look at the power table of 2, we can see that we have a base of 2 raised to some power x listed in this row, and it gives us some result. So like 2 to the second power gives us 4, 2 cubed give us 8, and so on and so forth. So we can see this relationship in our power table. We also should be able to note that as we increase our exponent by 1, this represents 1 additional multiplication of 2, because an exponent tells us how many times we are multiplying by 2. So we're able to go up and down our exponent table by multiplying by 2, or in the other direction, we could choose to divide by 2. And that will allow us to go either way we want, and it doesn't matter where we start. We could divide by 2 and go backwards. It's like subtracting 1 exponent, or we could multiply by 2 and go forwards. It's like it's like adding 1 exponent. So with that in mind, let's take a look at an example of one of the things the power table helps us to see. So we have our base of 2 to the power of x, and say we raise 2 to the third power, we're going to get 8. So the first thing we can say is 2 to the third equals 8. But we also have this relationship that if we speak in terms of logarithms, we can say log base 2 of 8 is equal to 3. So if we take the log of the base 2 of 8, we get 3. And that just tells us what power do we need to raise 2 to get 8, and the answer is 3. So this literally tells us what power we need to raise 2 to get that argument. There's one more relationship that exists here, and that is that this exponent tells us what root the base is of the result. So the cube root of 8 is equal to 2. So these three relationships all exist from the base to the power and the result. And this is going to come in handy as we investigate the product property of logarithms. And now before we do that, let's look back at the product property of exponents. We know that some base raised to some power m multiplied by that same base raised to a different power n gives us that base to the power of m plus n. And the power table helps us really see this. If, for example, we look at a base of 2 raised to a power of 1, so 2 to the first, and then that same base of 2 raised to a power of 2 times 2 squared, well, that's like having 2 times 4. And that'll get us, 2 times 4 gets us to 8, 2 to the power of 3, or 2 to the 1 plus 2. And this works regardless of where we choose to do this. So if we picked, for example, 2 to the power of 2 is 4, and 2 to the power of 4 is 16. So 2 squared is 4, 2 to the 4th is 16. Well, this should equal 2 to the 2 plus 4 equals 2 to the 6th, which is 64. And 4 times 16 is in fact 64. Because we're basically saying take 2 multiplications of 2 and then do 4 more. 1, 2, 3, 4. Getting us 2, 1, 2, plus 1, 2, 3, 4, aka 6 multiplications of 2. So that's where our product property of exponents comes in. And so this product property of logarithms here is going to be the same thing, but just in reverse. So rather than focusing on the exponents and doing rules with the exponents, it allows us to focus on the result. So what I mean by this is if we have, let's do green, log base 2 of, say, 2 times 4, well, our product property of logarithms tells us whatever's being multiplied inside the logarithm, we can split and add log base b of those different things. So this is equal to log base 2 of 2 plus log base 2 of 4. And so log base 2 of 2 is telling us what exponent we would raise 2 to get 2. And so that's a 1. Log base 2 of 4 tells us we need to raise 2 to the second power to get 4. And if we were to multiply this out, we would get log base 2 of 8, which is telling us we need to raise 2 to the third power to get 8. So 3 equals 1 plus 2. And so we have that exact relationship here. If we're multiplying the argument or the result, if we take this 2 and multiply by 4, this is really saying take one multiplication of 2 and then do 2 more multiplications of 2, and that's going to be 8, right? This 2 times 4 is also just an 8. And then what exponent would that result in? Well, it would result in the 2 was an exponent of 1. We had 1 multiplication of 2. And then this 4 represented 2 more multiplications of 2, getting us to 1 plus 2 more multiplications of 2, getting us to 8. And again, this idea is going to work no matter what numbers we choose. So if I want to go on my power table, and I want to pick some different numbers, and say I want to do, for example, log base 2 of 4 times 5. Oh, excuse me. Log base 2 of 4 times, say, 16. Okay. Well, our product property of logarithms tells us this ought to be the same as log base 2 of 4 plus log base 2 of 16. And the reason that this works is because if we do 4, that represents 1, 2 multiplications of 2, right? Log base 2 of 4 is 2. So this whole thing is just a 2 multiplications of 2. Then if I want to do log base 2 of 16, well, that represents 4 multiplications of 2. But I've already done these 2 multiplications of 2. So starting there, I'm going to do 1, 2, 3, 4 more multiplications of 2, bringing me to 64, aka 6 multiplications of 2, or 2 to the 6th power. So I'm going to add 4 multiplications of 2, because this represents 4 multiplications of 2, this represents 2 multiplications of 2, and we get 2 plus 4. If we look at this side here, log base 2, 4 times 16 gives us 64. Log base 2 of 64 is just 6. So 6 equals 2 plus 4. And of course, we know 6 is 2 plus 4, and that's sort of what this product property of logarithms tells us. It tells us that 2 multiplications comes from the 4, and then we multiply by another 4 multiplications. And when I'm saying this, I mean 4 is 2 squared, 2 multiplications, times 2 to the 4th, another 2 multiplications. And because this just represents the exponent, or the power, normally we would say, oh, we can just add these powers, right? With our product property of exponents, like we add the power of 2 and 4. 2 plus 4 gets us 6. But because this logarithm here actually represents the exponent, what we end up doing is saying, well, this is an exponent, and this is an exponent. So we're using that same property, but we're just adding the exponents, whereas log base 2 of 4, right? Log base 2 of 2 squared, here's that exponent, and here's log base 2 of 2 to the 4th, here's that exponent. And so here's our 2, here's our 4, and these 2 and the 4 give us this 6, because 64 is the same thing as 2 to the 6th power. So it allows us to break it up in this way. Let's take a look at a couple more. And let's see how perhaps negative exponents come into this. Having a good time erasing here. Okie dokie. So if, let's say, we want to do log base 2 of let's do 8, okay, times, and let's do 1/4. Okay, we want to know how can we split this up with the product property of logarithms. And so if we just use the product property, we can say it's log base 2 of 8 plus log base 2 of 1/4. Now log base 2 of 8 is equal to 3 because we need to raise 2 to the third power to get 8. And log base 2 of 1/4 is -2 because we need to raise 2 to the negative second power to get 1/4. Interestingly, we could also write this as log base 2 of 2 cubed and log base 2 of 2 to the -2. And so that's asking, what power do you need to raise 2 to get 2 cubed? And well, obviously that's the third power. And this asks, what power do you need to raise 2 to get 2 to the -2? Well, obviously you have to raise 2 to the -2 to get 2 to the -2. On the right-hand side of the equation, we know 3 plus -2 is just 1. And if we look back to the left-hand side of the equation, we can say log base 2. Well, I could choose to write this a number of different ways. I could choose to say 8 times 1/4 is 2, and then log base 2 of 2 is obviously 1, and we can show that this is valid. If I want to do this a little bit differently, I can show that this is log base 2 of 2 cubed times 2 to the -2. And what you'll notice is there's that 3 and there's that -2 that we have right here. Because this is representing the 3, this is representing the -2. And so inside that log, we could use our property of exponents, b to the n plus n, log base 2 of 2 to the first. That's saying what power do you need to raise 2 to get 2 to the first, and you need to raise it to the power of 1. Okay. So that's kind of how this property works. And so it can be useful for splitting up our logarithms, but it also can work just as well in reverse. So if I want to go in reverse, maybe I start with log base 2 of, let's say, let's do 1/4 again, log base 2 of 1/4, and say I want to add log base 2 of, let's do 16. Now, because these are relatively straightforward, we could just evaluate these from our power table, but we can also apply this product property of logarithms in reverse to condense this expression. So I could write this as log base 2 of 1/4 times 16. And then that would mean that this is equal to log base 2 of 1/4 times 16 is 4, and log base 2 of 4 just gives us 2. And so that's easy enough to see because we could say log base 2 of 1/4 is -2. We need to do -2 multiplications, or realistically 2 divisions, right? We're dividing by 2 and dividing by 2 twice to get to 1/4. And then log base 2 of 16 represents 4 multiplications of 2. So now starting at that point, we're going to multiply by 2, multiply by 2, multiply by 2, and multiply by 2. And so what we're going to get is 4 more multiplications of 2, giving us a total of -2 and then 4. So 2 multiplications of 2 is equal to 2 multiplications of 2. And one thing I want to note is I'm always starting here when I'm using this sort of moving along, because we typically think of 1 as being the starting point. That's no multiplications of 2. We start at 1. And so when I go 1, 2 in the negative direction, I'm dividing by 2 twice. And then I go 1, 2, 3, 4 in the positive direction, I'm multiplying by 2 4 times. If we were to look at that left-hand side a little differently, we could say this is log base 2 of 2 to the -2 plus log base 2 of 2 to the 4th. And so we could evaluate it this way and then still get -2 and 4, which does equal 2. Okay, So that's the main idea behind the product property of logarithms. It is the very opposite of the product property of exponents. So if I am to say, we'll do one last example to compare out here. Let's go back to this example. See if we can delete a little faster. Very good. Okay, so say we were to say 2 to the first times 2 cubed, right? And from our product property of exponents, we're able to say this is equal to 2 to the 1 plus 3, which is, of course, equal to 2 to the 4th. And so our product property of logarithms just does that in reverse. So instead, we say log base 2 of 2 to the first times 2 cubed, right, is equal to log base 2 of 2 to the first plus log base 2 of 2 cubed. Because this just represents the exponent 1. This just represents the exponent 3, right? 3 multiplications of 2 versus 1 multiplication of 2. But if we do this all together, well, in here we've got log base 2, 2 to the 1 plus 3, or 4 multiplications of 2. And so this whole thing just represents a 4, or 2 to the 4th power. Okay, so hopefully that was a little bit helpful, and hope you enjoyed the video.